Welcome back. What if we have independent researchers working on some context leading to some results, and a different group is working on omega leading to Q? We'd like to benefit from both schools of thought or both sets of programs. We'd like to bring them together. The idea is transparent at the beginning. We want P and Q. What would entail that? We can see that one way to entail P and Q together is to take gamma and omega as the premises. Premises are allowed to be plural, so there's no problem in combining them. But there is a problem when we actually try this out. We showed that for natural numbers, x is less than or equal to y implies x squared is less than or equal to y squared. We also found that that wasn't always the case for other number systems. If I took the same sentence to the integers, I could find numbers such as -5 and -3. When I square -3, I get 9. When I square -5, I get 25. 25 is not less than or equal to 9, so this was false. If we write down what we've just said in symbols, the natural numbers together with the integers would seem to entail a context in which P is true and not P is true, because that's the second one. This is a claim that's true in any logic. Once we have that this is false, we now have a problem. So how are we going to fix this? Let's imagine the context was drawn on a sheet of paper. Remember our previous video where we discussed that context could be thought of as a color of paper, and the statements we write on it would be the sequence that are true in that context. So what's happening here? The line is making a statement that's true on yellow paper, that is natural number paper. And the bottom line is making a statement that's true only on blue paper, that would be the integer paper. And we're now trying to find a piece of paper that's both yellow and blue. That doesn't exist. So we need to pull back and allow our logic to simplify rules that are true in only some spaces and still combine them together. So think of this as a color booklet where some pages are yellow, some pages are blue. We can still talk about them in the same book. To do this, we need to introduce a new type of logic called higher order logic. To tame that logic, we'll need some symbols. So let's start with those symbols. What the symbol I'll be using is called the element of, and it uses a little letter E to remind us of the word element of. We might also abbreviate it to in. The smaller letter is thought of as the data that we want to actually talk about in some premise. The larger data is trying to narrow the context. We think of this as being the yellow sheet of paper or the blue sheet of paper in our booklet of various premises. By putting in this restriction as notation, we're telling our readers that whatever's going to follow is a premise that's only true on the color of paper that is this larger alphabet letter, in this case S. So we could now write a sentence with the natural numbers in the rule of S and put that in as one page in a multicolored book. Let's see what that would look like. Using the sequent calculus, I'm now going to assume that we live in some new context. This context gamma is our booklet of multiple colored pages. In that context, one page is colored yellow for the natural numbers. And now if I take 2 points in this yellow paper, I can write the sequence sentence, x is less than or equal to y implies x squared is less than or equal to y squared. But only for those 2 x and y points that are elements of the yellow paper, the natural numbers. In the same booklet, elsewhere, I have different colored papers, and I can write different sentences. Let's see the natural numbers turned into integers. Here I've done the same thing, only I'm using blue paper by metaphor. I'm thinking that gamma, the booklet of all line colors, entails that x and y are elements of z. And when that's the case, then x less than or equal to y does not imply that x squared is less than or equal to y squared. Two things can be true at once if they're on different colored paper. By adding the symbol element of to my language, I'm able to draw out that distinction without throwing out an inconsistency. So it's a stronger type of logic. If I was to write the corresponding conjunction, it wouldn't be a contradiction. Let's simplify this to letters to see what that looks like now. Over here I have P with a natural number symbol on it. It's the statement that we were looking at before, but it's recognizing that it's on the yellow paper for natural numbers. Over here, I have not P, but with the integers on it. It's the statement P that we were looking at before, but the little subscript of the integers is reminding me that that's the new context. What we then get as a total context is that gamma entails P natural number and not P integers. If we stare closely, we see this is no longer a P and a not P. They're different flavors of P. This is only possible in a different kind of logic. This is not what the first order logic was. The logic we studied in the first few videos was first order. Every variable applied to everything. It was one sheet of paper. This is a higher order logic, multiple colored papers. So the same statement placed on different colored paper becomes a different statement, and therefore they can coexist without producing a contradiction. In anything you do, whenever you reach a contradiction, it's a warning sign that you need to add to your logic. Somehow you need to separate the differences out. Let's end with a bit of the jargon that you might encounter in other situations. This element of symbol is hard to find on a keyboard, and as an alternative, you might use the colon symbol, writing X:(S). We already saw this in our grammar lessons. When we had a grammar, say, of digits, we could take a digit to be accepting any one of the numbers digits 0 through 9, and we would write, say, the 8:digit. Another way to see this is that this was simply saying that 8 belongs to the color of paper that describes digits. We could then move on to natural numbers and describe something like 42:nat, meaning that it belongs to the grammar of all natural numbers. A further notation has more to do with programming language choices. For example, when you're typing on a computer, you might have so many different colors that it would be helpful to write them down with names, like writing the letter B instead of like writing the word blue instead of the letter B. It's more descriptive to the next person reading. And because of that, it might actually sound better to put the word before the letter. We could say integer n, or we might abbreviate that simply to int n. However you think of the different notations, these are specific to individual contexts, and you'll have to share them with all the people, just like we always have to share context. But keep in mind, we are doing something different than context now. We have added a higher order language. By writing in words like integer n, we are saying that we're limiting the scope of these variables to exactly that color of paper. The context now is the entire book that we might be writing. We don't necessarily know which color paper we will be using within that. So it's limiting it to sort of microcosms of local context. And finally, a little bit of jargon. The elements we already think of as the variables and constants that we would use in our standard sentences in first order logic. What should we name the things that are narrowing the context down, like the colors of the different sheets of paper in our book? One of the classical names is set, but there are several other names that you'll encounter too, such as in programming languages, you'll see the word type. And then there are further words like class, kind, and sort. Each of these exists because of a problem in describing everything we want to talk about using just one word. Remember how we ran into a problem when we combined the integers and the natural numbers? We had two different colors that needed to be brought together. Now imagine that we've made two books with different colored paper, which means that we need to be talking about things like books as being separate from the pages in the book. So if sets are the pages in the book, then sometimes we need to talk about books, meaning things that aren't pages themselves. We might move up to classes. We might even start to talk about the kind of classes. One class might be book. Another class might be bookshelves, which has many books on it. And then we could have a library, which has many bookshelves. You can see how this keeps scaling up. At some point, we might start to name things in kinds and sorts. These are all ways to try to explain to ourselves that we have this growing higher logic, that at some point, the things we have written do not have all the sophistication needed to talk about even bigger structures. So we invent new ways to keep growing. This is what's called a hierarchy. Sometimes it's called the cumulative hierarchy of sets, but it might also be called type theory and many other words that you might encounter. Don't be hung up on the precise names until you take very formal classes that make these distinctions important. For the average reasoning and programming, you can use these names interchangeably. Just be mindful that when somebody has an opinion on it, it may be based on some deep sciences in the background, or it might just be how they were raised. However it is, investigate, find out if it's important to know the difference. If they're casual about it, you can be casual too, and adopt a conversational language that you both enjoy. Until next time. That's how you take care of your chalkboard.